Hello. By now you should be familiar with polar coordinates, where x is written as r cosine theta and y is r sine theta. R is distance from the origin to a point, and theta is the angle counterclockwise from the positive x-axis. Alright, so polar coordinates. And by now you should be familiar that when you calculate the area of a graph in using multiple integration, double integration, then we end up integrating r dr d theta. So we write r as a function of theta, and so these limits normally come first, integrate with respect to r, and then integrate with respect to theta. It's a little easier, I think, to do it in that particular order. All right. Well, this part here can be easily justified, and you probably have seen the justification, perhaps. Imagine almost a square on the xy plane, and this is a distance of r from the origin. So this now this is infinitesimally small, so this side here we'll just call it dr. You know, the differential of r is infinitesimally small, and the other side of this quote-unquote square would be r d theta, because the arc length is r theta normally, radius times angle, but here the angle is a differential, so we write as r d theta. Well, so you can see that the area of this is approximated by r dr d theta, and there you go. And at the infinitesimal level, they're as good as squares, and the multiple integration in effect just adds them all up, all across the plane, goes through and sums all these infinitesimally small areas of squares. Okay. Well, I want to use a different approach for getting this, and what I'm setting up is a justification of the Jacobian determinant, which is useful for any coordinate system, any viable coordinate system. And so this is usually not proved in textbooks, and I really don't think my exposition here is going to qualify as any kind of formal proof, but it'll give you a pretty good idea why it works. And so anyway, I'm going to erase this and start fresh here. In rectangular coordinates, we imagine a little rectangle, dx, dy. Doesn't have to be a square, it can be a rectangle, but these are differentials, so it's at a very tiny level. And so the differential of area in general is dy times dx. No big deal. Okay, well, what would this look like with polar coordinates? And so if I do the differential of x dx, then I'm applying a derivative across here using the product rule, and but I'm going to write it as a differential. So I have the differential of r times cosine theta, so I'll write that as cosine theta dr, and then plus the differential of cosine theta times r. And so that's actually going to end up being a minus because of the derivative of cosine. So actually we'll end up with a minus r sine theta and then d theta. So minus because derivative of cosine is negative sine. Do that with dy, then we've got differential of r times sine theta, so that's sine theta dr, and then plus r times differential cosine, sine, so that's plus r cosine theta d theta. Alright, now, before I did this video, I just reminded myself why we don't multiply these together. If we multiply that together, we're going to get quite a mess. It would be, I'll just do it real quick, it'll be cosine theta sine theta dr squared, okay, minus r sine squared theta dr d theta, and then plus r squared cosine squared theta dr d theta, and then finally plus r squared cosine squared theta d theta squared. Alright, so imagine trying to integrate this. I suppose you could consider dr as squared as dr times dr, so you do integrate with respect to r twice. I don't know, what do you do with thetas? Okay, and so I think this is going to be pretty much a dead end. Trying to interpret this as literally this product. Alright, so I'm going to erase this, but I'm going to still use that. So here's what I came up upon. I'm going to think of this dx as cosine theta dri, and then minus r sine theta d theta j, and I'll call that the u vector. So I created a vector by just simply imposing an I here and a j there. Alright, so it's a vector, and on the plane, here's r theta. For example, r could be 2, theta could be 30 degrees. You could, you could literally define a vector. At every point in the plane, a vector is defined. And as a matter of fact, it creates its own vector field, because that's what a vector field is. Every point in the plane defines a vector. Alright, why am I doing that? Well, hold on. Let's do vector v, u and v. So here is v. Similar idea, sine theta dr, letter I, or vector I, plus r cosine theta d theta j. Alright? So, we kind of imagine that in the plane, every point is defining two vectors. And I'll just, make up something here. Suppose that u shoots off in this direction, and v shoots off in that direction. Okay. Now we really could draw these, physically draw these, with specific values of r and theta. We could, figure that out. If I create these two vectors, it creates and I'm kind of running out of board space, but there's a parallelogram here. There's a parallelogram, and the area of a parallelogram can be calculated by a determinant. And so here's what it is. The area, actually it's a differential of area because these are all infinitesimally small vectors. So that can be conveniently calculated for area of parallelogram with a determinant. And all I have to do is feed in the I and j components for u on one line, cosine theta dr, and then minus r sine theta d theta. I'm going to have to erase my little diagram here, at least that part of it. And then the bottom part is just substituting this line in, sine theta dr, and then r cosine theta d theta. Alright, so that would be the area. So imagine then that every point on the plane carries a coordinate that could be converted into r and theta. From x and y, each coordinate can be converted into r and theta, polar form. And each coordinate defines this infinitesimally small parallelogram. And it's going to vary as we move about the plane. And so the idea is that we get the area in the polar coordinate system by summing the areas of all these infinitesimally small parallelograms by doing integration, multiple integration. Alright, well, to cut to the chase, when you calculate this, you're going to get r cosine squared dr d theta. So let me write that out there. And by the way, let's, and it won't be a surprise what I get for this answer, but I'm going to call this the Jacobian determinant. And it may be proper to put absolute value bars on it. Now, this does not mean absolute value. In a matrix with absolute value lines, it means determinant, and that's a specific computation. But here, this means take the absolute value of the determinant. All right, so this would be r cosine squared theta dr d theta. So r cosine squared theta r, oops, one too many r's, dr d theta. And then, so this product minus that product, when I minus this product, the negative cancels, so I get plus r sine squared theta dr d theta. And you can kind of see where this is headed. If we factor out r d theta, we get cosine squared plus sine squared, which is 1. So this would simplify down to r dr d theta, which is what we're supposed to get. Okay, so anyway, I don't know if this was exactly what Jacobi was thinking about in the early 1800s when he came up with these with this determinant, but it works, and I want to expand upon this as we move along into other coordinate systems, and how do we calculate these determinants, Jacobian determinants. So anyway, all right. Now next I want to introduce the because my students have already seen polar coordinates, so I'm going to introduce the spherical coordinate system next. I know I promised to do spherical coordinates yet, but I think I better spend a moment on cylindrical coordinates. Now, if you're a student in my class, you've already seen some problems in cylindrical coordinates. But if you're out there in YouTube land, real quick, but I also want to justify its Jacobian. So cylindrical coordinate system is simply the polar coordinates with the z-axis added in. No change in the z-axis. So if you imagine a polar graph paper, it looks like concentric circles with radial lines. Looks like a big dartboard. And if you think of it this way, here's my polar plane with circles and radial lines. And if I add in the z dimension, the vertical dimension, then it just goes up and down. I have cylinders, concentric cylinders. And so that's the cylindrical coordinate system. Now then, the Jacobian for it, because I haven't really written out the Jacobian formally that well, so I wanted to get this in. The Jacobian would be partial x with respect to r, partial x with respect to theta, partial x with respect to z. And then down here, partial y with respect to r, partial y with respect to theta, partial y with respect to z. And it's an easy pattern to learn. We need this pattern to do other coordinate systems. And finally we have the z's, partial z with respect to r, partial z with respect to theta, and partial z with respect to z. There we go. So that's the Jacobian, and then we put that in the integral and multiply by dr, d theta, and dz to get the volume differential. All right, so when you plug these in, okay, so I've got, let me see, cosine theta, and then partial x with respect to theta was minus r sine theta. Over here, partial x with respect to z is going to be 0. Oh, that's pretty convenient for us. And down here, let's see, I've got sine theta, r cosine theta, and again a 0. Then we do the z's, partial z with respect to r and theta are both zeros. But here we go, partial z with respect to z is going to be 1. Alright, so there's a 3 by 3 determinant, which is the Jacobian, and it would come from taking these partial derivatives and assigning an I, j, and k vectors to each one. That would define a parallelepiped, and I'm not good at drawing these things, but anyway, there's a parallelepiped is I don't think I drew that very well. Anyway, it's think of it as a rectangular box. And well, anyway, it's a rectangular box that's been deformed. It's been squished. Imagine a cardboard box and you just started to shove it this way. That's a parallelepiped. It's like a parallelogram in 3 dimensions. And for each point on the XYZ space, we define an I, j, k vector. So we have a u vector, a v vector, and I guess a w vector. And the volume of a parallelepiped can be found by feeding those portions, I mean those, what's it called? Anyway, those components of each vector into this 3x3 determinant. Now, I've gone over this in my class before, so sorry if I'm not as complete as I would be in class with those of you in YouTube land. But anyway, that's where it comes from. Now, this determinant, when you do a determinant, and my class knows this, but the most convenient way to do this determinant is to do a cofactor expansion about either the bottom row or the right column. And so positive minus positive minus positive. If I expand about this column, then it's 0 times this 2x2 determinant minus 0 times this 2x2 determinant, and then plus this determinant, 2x2 determinant. Well, as you can see, those two cancel because of the zeros, so basically this ends up being 1 times this determinant, which was the determinant for polar coordinates. So basically this determinant, Jacobian, is r dr d theta, I'm sorry, it's just r, but when we integrate in polar, then we integrate r, dr, d theta, and dz. So we just add an extra integral and a dz, and we've got the volume. So the differential of volume is r, and dr, d theta, dz. All right, so now I'm going to move on to spherical coordinates. In 2 dimensions, we have two common coordinate systems are the rectangular and the polar. So we have x and y, which we use most of the time, and then occasionally we resort to polar, r and theta. Polar works great when things are rotated, and it turns out that sometimes it's much more convenient to compute integrals by going to a polar coordinate system if there involves some kind of rotation in the geometric figure. Well, in 3 dimensions, we have the rectangular system, x, y, and z. We have the polar cylindrical system, which is really the polar system with the z-axis added, so it's r, theta, dz. And then the third common one is the spherical coordinate system. And of course, it's based upon concentric spheres. So you have rectangular based upon boxes, x times y times z, rectangular boxes. We have the, or cubes you might say. Cylindrical system is based upon concentric cylinders, and then spherical is concentric spheres. And now there are other coordinate systems we can devise, and that's why it's important to learn the Jacobian. So we can devise other coordinate systems, and we may want to do some computations that may be pretty tough in other any of the regular coordinate systems. So anyway, the spherical coordinate system works like this. The spherical, let me make that legible. Spherical coordinate systems is rho phi theta. Okay, let me make sure I got that in the right order. I'm pretty sure I do. Yes, they're in the right order. Rho, phi, and theta. I'm doing this video on the fly, and I haven't taught this for 2 years, so just want to make sure. What in the world does this mean? Okay, well, rho is the distance from the origin, 0, 0, 0. Okay? Well, how do you figure that distance? So here we are in the 3-dimensional plane, and there's a point out here, x, y, and z. It's kind of hard to imagine exactly where that is, so I could go up here, over there, and up. Okay. Here, let me draw that in. Let's go with, if I start at the origin, go forward x, go right y, and then go up z. There we go. That's x, y, and z. And So the straight line distance is rho. Rho. So please don't write a P. It's the Greek letter rho. So this is, of course, a cursive P with a little lip here. But in Greek, rho is just curled over like this. All right. So then the x squared plus y squared plus z squared equals rho squared is actually the equation for a sphere of radius rho. And if we take out the z's, it looks like the Pythagorean theorem. And in 2 dimensions, that would be the equation of a circle. So when you add the 3rd dimension in, you're calculating the square of the distance from the origin is the radius of the sphere. All right, so this is that's the conversion. When you go from rectangular coordinates to spherical coordinates, you want to use x squared plus y squared plus z squared equals to rho squared. Well, I'll write that up later. So now then, theta is the same theta that you find in, I'm supposed to use phi next, aren't I? Okay, well, let me do theta. Theta is supposed to be the same theta that's used in polar coordinates. It's an angle that's rotated in a horizontal from the positive x direction. So we'll call this as the x, y, z space. So the flat floor is the xy plane where z equals to 0. And theta, let's see if we can find another color here. Theta, no ink in that one. And I'll try another purple one. Okay. There we go. Theta swings over horizontally from the x-axis. So I come out well, I don't know. What sequence do you think of this in? I don't know. But we've gone out a distance of rho. We've swung over theta, and now we rotate up. Actually, we rotate down, okay, because the angle from the z-axis is phi. All right, so let's get that down here. Theta, and to do it in proper order, I suppose we should use phi next. Phi is the angle of rotation from the z-axis, and it's a positive z-axis. I didn't write positive, but positive z-axis. So phi rotates downward like so. Okay, and then we swing over sideways to catch theta. So theta is the angle of rotation horizontally from the x-axis. Okay, I didn't get too formal there. It's the counterclockwise rotation from the positive x-axis. I guess you want to be really complete here. All right, so we can find any point in space by connecting to it with rho. We can find the angle that is horizontal, swinging this way, and then the angle that's vertical, that swings down, and that's your alternate system, rho, phi, theta. All right. So now then, what in the world do you make of it? Okay, so let's see, kind of winging it here. Let me do some erasing here. Well, I believe I got this figured out. It's always a little mind-boggling trying to figure out how to go from x, y, z to spherical coordinates when you haven't done it for 2 years. So let's see. I think z is going to be the easiest to see. So I'm going to start off with z. Now imagine this this little rectangle here, and I'm going to draw it out. Of course, the rectangle has swung out somewhere in the middle here. But if we look at it, its profile, then here's Z. That's a right angle right here. And this is my angle phi, rotated down from the Z-axis. And my distance from the origin is rho. So we look at this triangle, we see that Z is equal to the rho cosine phi. That's all there is to it. So the cosine of phi is adjacent over hypotenuse. So it's Z divided by rho is cosine, multiplied by rho, and Z equals cosine phi. All right, that's one coordinate down. Now, to do the x and y, all right, I want to think about this coordinate here. Where does x come from? Well, I need to go through this triangle right here. Now, this triangle has a, I suppose I'll do that in, running out of colors here. That's a right angle there, because we're going from the XYZ plane straight up, from the horizontal straight up, so there's the right triangle. And when you look at that triangle, we've got some kind of base. Whoops. We have a base of the triangle. We have a height, which is Z. And we have a hypotenuse, which is rho. And this angle right here is not phi, because it's the complement of phi. So from the z-axis down to the horizontal is 90 degrees, or pi over 2 radians. So this angle is going to be the complement. It's pi over 2 minus phi. All right. So I hope you can read that there. It says pi over 2 minus phi. Literally 90 degrees minus phi. All right, and this side is that distance there, which, well, it looks like r, doesn't it? I'll call that r. Okay. And it is r. In the horizontal plane, this distance is the same as r from polar coordinates, isn't it? All right, so what do we got here? And what am I trying to get? Well, when we look at this triangle here, now I'm looking at the base triangle, and the base triangle, that's a right angle there. So it's just fun trying to fit this on a 4-foot by 3-foot board. So this triangle I'm going to put up here, and I've got let's see, the kind of mind-boggling here. Here's x and y. Seems like that's backwards, isn't it? Here's x, here's y, here's r, and there's my right angle. And but this is angle theta up here. There's theta. Okay, so x from here would be, okay, it's cosine r cosine theta, which I suppose we could have borrowed from polar coordinates, couldn't we? Because the cosine of theta is adjacent over hypotenuse. X is r cosine theta. All right. Now then, if I can put all this together, and the r, let's see, if I take the cosine of this angle, the cosine of pi over 2 minus phi would be adjacent over hypotenuse, so that's r over rho. And now here's the thing. The cosine of pi over 2 minus phi is the sine of phi. All right, so this is kind of easy to figure out that the cosine of an angle is equal to the sine of its complementary angle. And so this is literally just sine phi. There we go. Now then, so where are we at? R from here multiplied by rho. R is rho sine phi. Okay, so one of these days I'm going to get a bigger board, so this is not quite so jumbled all over the place. But if I replace r up here with rho sine phi, I've got my, and I'll erase this, I've got my x. X will be rho sine phi cosine theta. There we go. And if you do all that stuff with the y-coordinate instead, you'll end up with a y is r sine theta instead. So what you end up with is x equals to rho sine phi sine theta. So there you go. I have it in a little bit different order. It should be in x, y, and z order, but these are that's how you go from polar coordinates to rectangular coordinates. Now going backwards, what do you do? Well, one thing is that we know that that rho squared, for example, is x squared plus y squared plus z squared. Okay. So if I want to convert from rectangular to polar, rho is easy to calculate. It's the sum of squares is the square of rho. And you can also take advantage of this. X squared plus y squared is r squared. So you can say, well, this is r squared plus z squared, if you're thinking in terms of polar coordinates. And hopefully I'll get an example where I'll show you where this is good thinking. Okay, this is advantageous to sort of combine polar coordinate thinking with the spherical coordinates. All right, specifically to get theta and rho, we would have to solve these equations as various ways. For example, theta would be the inverse sine of y divided by rho sine phi. Okay, so that would be messy, wouldn't it? That would be pretty messy. And particularly if you're not in the first octave where everything's positive, then it's just gonna, now you have to think about what's negative, what's positive with that. It's all a big mess. So anyway, there's our spherical coordinate system. And before we attempt a volume integration in spherical coordinates, I want to derive the Jacobian, which will allow us to do that integration. So I'm going to erase the board and start fresh with that. And here we go. I wrote these in the proper order. Again, x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. So make sure you have that in the spot. I don't memorize that too well because I don't do this constantly all the time. So, but I've got it back in my head now, and you need to either get it in your head or at least have it by you where you can refer to it. All right, so there's our spherical coordinates system. And now then, in order to integrate in spherical coordinates, we have to do a triple integral, and we have to calculate the Jacobian. So the Jacobian will be partial x respect to, what should I do first? Who knows? Phi? I'll get the angles first. Partial x respect to theta and partial x respect to rho. Then we have partial x respect to phi. Oh, partial y, I'm sorry, that's a y. Okay, respect to phi, partial y, respect to theta, partial y, respect to rho. Finally, partial of z, respect to phi, partial of z, respect to theta. Are you asleep yet? Partial of z, respect to rho. Alright, well, the Jacobian determinant is just a pattern. You can see the pattern. I've got my rectangular coordinates going across the top, so I have my new coordinates down below. And now to fill that in, okay, we'd have to, of course, take all these partial derivatives. And I think I'm going to leave that to you. It's not hard to fill this in. And it's a mess, okay. Now you have to calculate a 3x3 determinant. And we've done that in my class. If you're out in YouTube land, you probably have an idea how to do that from doing cross products of vectors. Alright, so the Jacobian ends up being, I think I know what it is, but I better look it up just to be safe. And it looks like it's rho squared sine phi. Yeah, so this all boils down to, it takes a bit of work, but you get a lot of simplification with cosine squared plus sine squared equal to 1. That shows up probably a couple of times here. Anyway, it boils down to rho squared sine phi. So there it is. That's the adjustment. That's the adjustment. So like we did earlier before, if we had a point in space and we created 3 vectors to form a parallelepiped. Okay, so does that look like a parallelepiped? Okay, it's a box that can be squashed or distorted. And so you imagine that, where's my red pen? Here we go. Imagine that we can create a differential vector going this direction and one going this direction, which forms that side of the parallelepiped, and we have this one right here. So each of these vectors comes from one of these lines where you have I, J, and K vectors. They kind of resemble, by the way, I don't know if I can't remember if I pointed this out, these vectors kind of resemble what you would get by using the gradient. It's kind of like using the gradient on this to create vectors. And the volume of a parallelepiped you can find by taking the components of those vectors and feeding them into there. So that's where it came from, and it's, to me, a big deal to spend some time on this, because you want to be able to apply this to other kinds of coordinate systems, custom-made coordinate systems. So there we go. So I'm going to erase everything and work a problem or two with spherical coordinates. Learning how to do calculus with spherical coordinates is a very traditional multivariate calculus experience topic, and but I don't want to oversell it. The drawback with spherical coordinates is that there really aren't very many practical problems to apply it to. However, it's very instructive and opens up the possibility of creating custom-made coordinate systems, and for that purpose I think it's well worth learning. Anyway, I'm going to start with a kind of a no-brainer when it comes to applying spherical coordinates. Let's find the volume of a sphere. Now, Archimedes figured this out without calculus, without algebra. He figured this out over 2,000 years ago. I no doubt Archimedes was thinking in terms of calculus as far as the ideas of limits, and but nevertheless, quite an accomplishment for over 2,000 years ago, considering the primitive nature of math at that time. Anyway, let's come up with a sphere, and I think I'll make this one with a radius of capital R. So I'm just going to draw it in the first octet, but of course it's a sphere, covers everything. So radius of R, capital R, and in terms of x, y, z coordinates, the distance from the origin to the edge is constant. It's R. And so applying the Pythagorean theorem a couple times, you get x squared plus y squared plus z squared equals to r squared. Now, I want to show you what this looks like for the fun of it, what it looks like in rectangular coordinates. If we solve for z, z would be the square root of r squared minus x squared minus y squared. Now, this is only the top hemisphere, by the way, because when you solve for z, you have to take the square root, and you get plus or minus square root. So the negative square root is going to be the bottom half of the hemisphere. This is the top half. All right, so there's our first limit of integration. So our volume of a sphere. I'll tell you, once you see this thing set up, you really tend to appreciate the spherical coordinates. All right, so if we go with z first, I'm going to I could integrate from negative square root to positive square root. In other words, from the bottom hemisphere to the top hemisphere. I think I'm going to just do the top. 0 to the square root of r squared minus x squared minus y squared. Now we have to keep track of adjustment here, because already I need to double this integration in order to get the this integration so far in order to get the proper volume. Now, once you integrate in the z direction, you collapse that dimension. And when this collapses, what you see is a projection that gives you this circle. And the circle is now x squared plus y squared equals to r squared. So at that point, if we choose to integrate with respect to y next, dy, then I could integrate from the y's. Remember, this is the y-axis, positive y-axis. I could go from 0 to this edge. So I have to solve for y, 0 to square root r squared minus x squared. But now I've neglected the back half. So I've only got 1/4 of the sphere. And finally, when we integrate the y dimension out, we collapse the y dimension, and all we're left with is a segment projected onto the x-axis. And if I carry on with positives, I'll go from 0 to r for the x-axis. So as you can see, it's a continual collapsing of dimensions that produces this integration. And because I've taken progressively half each time, basically this triple integral is only integrating in the first octant, the first 1/8. So I'm going to have to multiply by 8 in order to get my calculation for volume. Well, it's not a lot of fun because now we can integrate dz and we get z from these limits, and so it ends up with a double integral. And inside I've got now the square root of r squared minus x squared minus y squared dy dx. All right, now proceed from here if we want to stick with rectangular coordinates. What am I going to do? I'm going to have to use a trigonometric substitution. You know, this has the form of something like r sine theta, so we have to go with a trig substitution here. And I guess way too messy. I've done this for 4 and 5 dimensions before many years ago, before I figured out I could create a larger spherical coordinate system. So let's don't reinvent that wheel. All right. So anyway, that's what we're up against. This is going to be a mess. It's going to be a mess. And if we stick with x, y, and z. Now let's go with spherical coordinates. Now we could do this with cylindrical coordinates. It works very well. And I think I did that in class, if I remember right. But anyway, in any event, we're talking about spherical coordinates here, so let's do that. All right, let me erase all this mess. Okay, well now then, how do we go with spherical coordinates? Well, it's quite a bit different process. Now, for one thing, this is literally rho squared equals to r squared, and so rho equal to r is the equation for a sphere of radius r. So as you can see, that's very nice. Rho equal to r, couldn't get easier, to a constant. All right, so that's the equation of the sphere. Let me write that in. Rho equal to r. Okay. Now then, when we integrate this thing, we have to use the Jacobian inside. That was rho squared sine phi. And let's go d rho, d phi, d theta. All right. And we could probably switch these around a little bit, but I'll just go with that order. It's kind of the typical order. All right. Now, when it comes to calculating this volume, I'm going to integrate rho from 0 to r. In other words, we're going to count the radius going from 0 to a radius of capital R. So rho runs from 0 to capital R, which is very nice because there are no variables here, just the constant R. All right, as far as phi, let me say, yeah. I'll tell you what. Let's yeah, we can do it that way. As far as phi goes, I don't want to, remember, phi equals 0 starts pointing at the zenith, up the z-axis, positive. And phi rotates down, and if I rotate down 180 degrees, I've rotated half of the sphere. Now if I've rotated 360 degrees, I've covered a whole sphere. we got to be real careful here, because I also have to think about theta. Remember, theta goes horizontally this way. All right, so if I take phi from 0 to 180 degrees, and I have to go with radians, so 180 is pi radians, then I have taken basically this half circle. Okay, now imagine this. We went out to the edge and we rotate down. That's a half a circle. And then theta in that case would spin 360 degrees, or 2 pi radians. So theta would be 0 to 2 pi, like so. So now if you rotated 2 pi or 360 degrees with with phi, if you do this and then spin it completely around 360 degrees, you're going to end up getting double the answer you should be getting, because it double counts. So by going from 0 to pi and then spinning that half circle around 360 degrees at 0 to 2 pi, we'll get the correct answer. So this is the peril of using spherical coordinates, is making sure you're accurate in how you choose your angles. Basically your angles. All right. Well, there you have it. This shouldn't be too tough. How tough can it be? So I'm going to erase the sphere so I have room to complete this integration. Well, here we go. I've got my integral. I wrote it up here. And we integrate rho. I'm going to hold sine phi as being constant, and I'll get rho cubed over 3. So we have 0 to 2 pi, 0 to pi, and then rho cubed over 3 sine phi from 0 to r, and then d rho d theta. Okay, and for the moment, sine phi is a constant, so I just plug r in. I get r cubed over 3 minus 0. So that allows me to factor out the constant r cubed over 3. And I'm left with this, integrating sine phi, d theta. Okay? Now, and already you can tell we've got the correct units, because r is length, and length cubed is volume. So that's the correct units. These are dimensionless. The angles are dimensionless, so they do not contribute to any addition of dimension. All right, so integrate sine, we get negative cosine. So I have r cubed over 3, 0 to 2 pi, and here I've got negative cosine phi, evaluated from 0 to pi, and then d theta. Well, when we plug in our limits here, we'll get negative cosine pi minus negative cosine 0. And what is that? Well, this is minus negative 1, 2 negatives cancel here, plus cosine 0 is 1. So I end up with 2. That ends up being 2, doesn't it? When we plug those limits in. So this would give us 2r cubed over 3. And now I'm integrating from 0 to 2 pi of d theta. And that's easy. We'll get theta. I'll write it out. 2r cubed over 3. And then we have theta from 0 to 2 pi. Well, when you plug that in, we just get 2 pi times 2 is 4 pi r cubed over 3. So we end up with volume is 4 pi r cubed over 3, which is just what Archimedes got. And that's, of course, is the correct expression for volume of a sphere. So anyway, I'll come up with another spherical coordinate problem. Okay, well, here's one of my favorite spherical coordinate problems, and I call it the volume of a bagel. So if you take a circle, and this circle has radius 1, but the center is at 1. It's actually, the center is on the circle of radius 1. Okay, so here's x, here's y, and z. And it's rotated, spun around, so I've got a circle over here, and this, you can kind of imagine this is a a donut without a hole, which I call a bagel. All right, so a circular torus. Torus is a donut-shaped object where the circle has been rotated. However, the radius is 0 rotation here. There's no hole to it, so I call it the bagel. All right. Well, anyway, and spins all the way around. What's its volume? Okay. Well, I'm going to erase this extra stuff here and recopy my original diagram. This is one of my favorite spherical coordinate integrals. Find the volume of what I call a bagel. All right, so imagine this circle, radius 1, and it's centered at 1 over here so that the edge is at the origin. And it's been rotated around the z-axis. Now, this is not a particularly challenging problem. In Calculus 2, we do volumes of rotations. And I think probably we could use cylindrical coordinates on this problem. But it's kind of fun to try with spherical coordinates, so this is one that's not necessary to use spherical. However, I think we learned something from it. There's something to be gained here. So I won't draw the picture, but imagine this is spun around. Now if you take a circle and spin it around, you create a donut-shaped object, and we call the torus, okay? And it has a hole here, but this one has no hole, so I call it a bagel. What's the volume of our bagel? Using spherical coordinates. All right, so very instructive problem. Now, this starts off with x, y, z coordinates, and we say, well, what's that circle in the y-z plane? It's been, the circle at the origin has been shifted to the right, so it's y minus 1 squared plus z squared equals to 1. Great. However, it's in x and y plane. Actually, if it's over here on the side in the xz plane, it would look like x minus 1 squared plus z squared equals to 1. That still doesn't help us tremendously, because what about when the circle is out here at some angle out in between? Yeah, here's where I think I started thinking a little creatively here, and think, well, because we're spinning horizontally, think polar coordinates. What if we said this is r? Okay, r goes from r is 1, because the equation r equal to 1 literally is a circle of radius 1. And so let's see, could I write this bagel out this way? And it turns out if I write r minus 1 squared plus z squared equals to 1, that describes the bagel. And so we've got, no matter how it's spun, the distance from the origin horizontally outward to 1, that's measured by r. So r minus 1 squared plus z squared equals to 1. So anyway, that's it's a good start there. We've adapted the polar coordinates to this problem, which I want to do with spherical coordinates. All right, now what in the world is this? R, well, let's see. Remember that x is rho, how's that go? Sine phi cosine theta, and y is rho sine phi sine theta. And z, we'll just get it down, rho cosine phi. All right, now r squared is x squared plus y squared. So if I substitute here, I'll get rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. So it's a little bit illegible. Rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. And as you can see that if we factor out rho squared sine squared, we get cosine squared plus sine squared, which is 1. So r squared is equal to rho squared sine squared phi, which means that r is rho sine phi. Okay. And we probably could have done that with trigonometry, but using these equations, we can get r as rho sine phi. So isn't that interesting? Because rho cosine phi is z, but rho sine phi is r, distance from origin horizontally. All right, I'm going to erase this mess so we have room to work, and plug it into here. Now this will give us, when I multiply this out, is r squared minus 2r plus 1 plus z squared equals to 1. And then of course the 1's cancel off, leaving a 0 on the right side. And then if we substitute, I've got rho squared sine squared phi minus 2 rho sine phi plus, and z, remember, is z is rho cosine phi, so square it, we get rho squared cosine squared phi. That equals to 0. And then these two, combine them together, factor out rho squared, you get sine squared plus cosine squared, which is 1. So I end up with rho squared minus 2 rho sine phi equals to 0. Well, now what? We have to solve for rho. Now, if we factor out, we have rho times rho minus 2 sine phi equals to 0. And by factoring, yeah, rho can't be 0. That would be trivial. Rho can't be 0. So I can ignore my trivial solution and solve this, and rho equals to 2 sine phi. So there you go. The equation of the bagel is rho equal to 2 sine phi. So there's some good trivia for you next time you go into a donut shop. Please bring me 2 sine phi, please. Rho equals 2 sine phi, and I would like cream cheese with that. All right. I don't get to do too many jokes, so I've got to take advantage of them while I can. Now then, that's my equation, which is convenient because when you solve rho in terms of phi and theta, then we can integrate rho. So we want rho as, and by the way, rho is, I don't think I've pointed this out yet, is RHO, is rho, not ROW, RHO. All right, where was I at? If we're going to integrate with respect to rho, we want rho, first we want rho to be a function of phi and theta. And preferably phi is enough. Okay. And we're lucky here, we don't need no theta in that function, so that makes it easier. Well, let's set up the integral. Well, here we go. I took the 8 pi over 3 and a 2, made that 16 pi over 3, factored out. I took sine to the 4th phi and thought of it as sine squared squared. Now sine squared phi, using the half angle formula, sine squared is 1 minus cosine 2 phi over 2. Then we had to square it because it was ultimately 4th power. Now then, when you multiply this out, I'm going to get a 4 down here. The 4 cancels the 16. I get 4 pi over 3. And multiply this out, I get 1 minus 2 cosine 2 phi plus cosine squared 2 phi. So I need to use the half angle formula again. Now cosine squared becomes 1 plus cosine of the double angle. So now we have 1 plus cosine 4 phi all over 2. And now we integrate this. Okay, I got my 4 pi over 3. And here I've got 1 plus 1 half. That's 3 halves. So I have 3 phi over 2. 3 halves phi. That took care of the constant. And then integrate this. We get, I think it's sine 2 phi. So you take that derivative, you get 2 sine, oh, it's going to be a minus, isn't it? Minus sine 2 phi. Alright. Go backwards, take this derivative, I got minus 2 cosine 2 phi, then times 2, chain rule. So that works. And then finally, integrate this, and we get plus, sine 4 phi over 8. So if I take this derivative to check it, I'll get cosine 4 phi, and then times 4 over 8 is 1/2. So looks right to me. And no one's here to argue with me, so I suppose that's the way it is. And if we plug in pi, well, if I plug in pi here, I get 2 pi and 4 pi. Those signs are zeros. Of course, if I plug in zeros, those signs are zeros. So all that goes. And we end up with 4 pi over 3 times 3 pi over 2. And let's see, what do we get there? Looks like 2 pi squared. 2 pi squared. Cubic units. Alright, so, yep, that's it. Volume is of the bagel, radius 1, is 2 pi squared units. So, anyway, I suppose you could use that at the donut shop too.